Hello, everybody. I'm Abhinaya from Team Amanda. Along with me, we have Jessica and Neil. Today, as part of geometric modeling presentation, we are going to start with very first topic, curve and surface basics. I'm sure that few terminology is known to everybody like curve, spheres, solids. So let's get started. Here is the topic division. So I'm going to explain first three concepts. First of all, I would like to know where do we use this geometric modeling? So it is used in various sectors like industrial engineering, automotive engineering, aerospace, defense, robotics, medical imaging, and visualization fields. Basically, simulation is typically time consuming, so every industry, is moving to state of art software to easily design minute details of surfaces. So here comes the first picture. So aeroplane. So while designing the aeroplane, we use geometric modeling. We do have surface at the edge of plane of wings. So this is called winglets. Winglets basically helps to consume less fuel and reduce the community noise. Such minute curves can be designed using geometric modeling tools. And second picture is in medical science field. So if you observe in medical industry, we have lot of surgical equipment to serve very special purpose. So I chose a simple needle here, so which has three wires placed in the XY plane. So you can see in the big picture of it. So it has three wires in XY plane. So this needle has little curvy shape at the edge of it. So as you can see, so this is the edge of needle. So such minute detail also can be designed by using geometric tool. So if you observe right from the big object to the small minute part, we can design by using geometric modeling. So here is the basic definition. So the curve is a point of motion. So as you all know, sine curve and cosine curve. So it is basically a point of motion. And if you come to the surface is one dimensional bigger than the curve. So which is in three dimensional motion. So you can see here the design of surface is the combination of the curves. So you can see front side view and the bottom view of the surface. So we use curves and surfaces in many applications like data plots, artistic sketches, and CAD tool. So how do we represent these curves and surfaces? We use two forms. One is implicit form and second one is parametric form. So we'll see those two forms here. The first one is implicit curve equation. So we represent any curve in the form of f of x comma y is equal to constant. So basically, it gives x and y dependency in this equation. So coming to the second notation, parametric form of equation, we have um, the equation form as you observe here. So it is in the form of x and y. We don't have any combination of both x and y. So we have independent representation of x and y here, and x and y are dependent on u parameter. So u parameter is basically ranges from a to b, and this a b is basically 0 and 1. So u lies in between 0 and 1, and this parametric form can be represented in multiple forms. So here is the example circle. Circle is basically formed by using origin and a constant distance from the origin. And the first left part is implicit equation of the circle, which is in f of x comma y notation, and the parametric representation is in the form of x and y. So x of u is cos u and y of u is sin u. So this is parametric representation of the circle. And if we do the derivative of parametric form, we'll get the velocity and acceleration. The first derivative produces the velocity of the particle, and the second derivative produces acceleration of the particle. So we have two terminologies here, uniform parameterization and non-uniform parameterization. Uniform parameterization is basically the magnitude of the velocity. So when we do the magnitude, we'll get 1. That means we have constant speed here. And in non-uniform parameterization, you can observe that at time t equal to 0, we have acceleration is 2, and at time t is equal to 1, we have acceleration 1. So basically, as time progresses, we have change of acceleration, which leads to non-uniform parameterization. And coming to the surfaces is one dimension bigger than the curve. So you can see this is a sphere equation which is having horizon is the center of sphere. So the representation of sphere is x square plus y square plus z square minus 1 is equal to 0. And we can represent this surface in terms of implicit form and the parametric form. So here is the parametric surface. So parametric surface uses two variables u and v. So and the representation goes here: x of u comma v, y of u comma v, and z of u comma v. Again, we can derive the parametric form partial derivation with respect to u and v. So when we do the vector cross product of any point which lies in the surface, which produces a constant value. So we have seen two representations, parametric form and implicit form. So which representation is better? So basically, universally accepted form is parametric form. So parametric form, as you can see, it's independent of both x and y. So it's more easy to extend to the higher degree when compared with the implicit form. And again, parametric form doesn't have any error during the representation, and even parametric form is computer friendly because it represents in a vector form. So parametric form is slightly universally accepted form when compared to the implicit form. Based on the suitability of the application, we can either go for implicit form or the parametric form. So parametric form is better when we have curve and surface, whereas implicit form is better when we have to compute at any particular point. So if you observe that this is the first representation of the car and this is the another representation. So the first picture is world's slowest car and this is the world's fastest car so far. So as you can see the surface of the first image and the second image surface. So the second image surface is free form and which has very great aerodynamics when it is moving when compared to the first surface here. So when air is flowing, when this car is moving, so air will hinder, the mirror hinders the airflow, so it goes with very slow velocity when compared to the second image. So we have another ideal representation of the function for parametric form by using power basis form. So basically the ideal function will have 4 points. So the ideal function should be very computer friendly and which requires very little memory for the storage, and it should have very less floating point errors, and it should be very easy representation when compared to the other function. So we are taking the ideal function as polynomials here. So we'll see how do we represent polynomials to design curve and surface. So polynomials can be represented in two forms, power basis form and Bezier form. Power basis form is full of algebraic equations and Bezier form is a geometric form. So first we'll see power basis form here. So the nth degree power basis curve is represented with summation from I 0 to n and product of a of I and u power I. So a of I is a vector, so which is a vector of xi, yi and zi. So xi is again summation from I 0 to n xi into ui. We have another representation of power basis form in the matrix notation. So here it's a product of a row matrix and the column matrix. So we have ai here. So ai is basically the uh, product of c power c of I u, the partial derivative with respect to u by I factorial. So we can represent this power basis form in terms of line, parabola. So when n is equal to 1, we'll get line in power basis form, and when n is equal to 2, we'll get parabola. So you can observe both the curves here. So line is starting with a0 to a0 plus a1, and parabola is having a0 to a1 plus 2a2. So these are the representations in power basis form, and when n is equal to 3, we can produce cubic. So as you observe the cubic form, the endpoints are lying in different planes, and we have twisted curve also. So we have one more concept here as inflection point. So when you just draw tangent through the inflection point, both curve and the tangent both will merge to each other. So this is the importance of inflection point. So we have drawbacks in power basis form. Basically, power basis form gives only one starting point, but designer have to get 2 points. So this is the drawback of power basis form. And we have one more drawback is it prone to the round off error when coming to the floating point thing. So Bezier curve overcome these deficiencies. So we'll see in the Bezier representation. So Bezier representation, this is the basic general representation of any curve. Bezier representation is basically the product of two things. One is blending function and second one is the control point. So we'll see how to produce these Bezier curves. When n is equal to 1, it's a linear one. So we have blending function here. So based on the blending function, we can substitute in the main equation in C of u. So we'll produce with this equation. So when we just draw the equation with P naught and P1, we'll get the linear one. When n is equal to 2, after substituting in these two formulas, we'll get the equation of parabola. So as you can see this diagram, which is having endpoints p0 and p2. So visually you can see here so how this curve is drawn. So the first one is linear, it drawn from p0 to p1, which is a straight line. When we have n is equal to 2, we can draw parabola. So parabola is drawn basically with endpoints p0 to p2. As you can see, the intermediate point is p1. So we have one basic concept here, which is a control polygon. So you can see a triangle which is a control polygons here. So when you just move these control points, you can define this curve along with this control polygon. So when n is equal to 3, as higher dimension goes, with 3 points, with higher degree n is equal to 3, we can draw a cubic curve. So again you can see the control polygon, and when n is equal to 4, we can draw quartic polygon. So we have a basic property here, convex hull property. When you just define a curve, so the curve lies inside the polygon, which is called convex hull property. So again visually you can see here how we can draw the curve formation along with the control polygons and control points. So we'll see the animated form of uh, Bezier curve here. So which is so interactive. As you can see the control points and control polygon, if I just move this control point, you can see the different shape of the Bezier curve. So we can play with these control points to design n number of Bezier curves.
All right, let's talk about some Bezier curve properties. The first Bezier curve property that we will go over today is actually one of the most important one and one of the most well-known one as well, is the non-negativity property. This property states that all basis functions are non-negative due to the domain of u being in the range of 0 and 1. Since the domain of u is in the range of 0 and 1, which is a positive range, all the basis function has to be positive as well. The bolded mathematical equation written at the bottom right underneath definition is the mathematical representation of this property. The second property of Bezier curve is partition of unity. This property states that the sum of the basis functions at a fixed u is 1. So when you have a bunch of basic functions and you break them all up and you get numbers and combine them back all up together, it's going to end up being equivalent to 1. So if you look at the image on the right, the bottom one, you could take a look at all those basis functions. So every single line there in all the different colors, those are all different basis functions. And if you look at the right side, you will see little segments of line in different color that are representative of the basis function. So as you can see, when you add up all those color lines together, it ends up equivalent out to being equal to 1. And then if you look back to where the definition is, if you look right underneath there, the bolded black mathematical function there is the mathematical representation of this specific property. The third Bezier curve property is endpoint interpolation. This property states that the curve begins at the first control point and will end at the last control point. So if you have a bunch of control points, then the Bezier curve that's created out of all those control points, the beginning of the curve is going to be at the first control point, and then the end of the curve is going to be at the last control point. The fourth Bezier curve property is symmetry of basis functions. This property states that for any n, the set polynomial is symmetric with respect to u equal 1/2. So basically, in other words, this is saying that the Bezier curve is going to be symmetrical if you split it up in half. And the idea of this is that if you have a set polynomial written all out from like the first control point to the last control point, if you reverse the order and write it backward, so if you start writing from the last control point to the first control point, the Bezier curve that's going to be created is going to be the exact same either way in both order. This is what the symmetry of basis function property is saying. Another property that we're going to talk about is the convex Hall property. This property states that curves are contained in the convex halls of their defining control points. So now let's take a look at the drawing on the right. All those blue dots are control point, and then the light red line that connects those blue dots is the control polygon. The gray area that is created by connecting the outermost control point is the convex Hall. So the definition of a convex Hall is basically the biggest area that you can create by connecting the control points together. So in this example, that gray area is the convex Hall. And then the dark red line is the curve that we have created from these control points. So as you can see here, the curve is contained within the convex Hall of these particular set of control points. And if you look at the image at the bottom on the left, you can take a look at P0, P1, P2, and P3. Those are our control points. And then the polygon that's created by connecting those control points is the convex Hall. And as you can see, the curve that's created by these control points is also contained within that convex Hall. This property basically shows that the generated curve will be in an understood and computable region. Alright, the last Bezier curve property that we're going to talk about today is variation diminishing property. This property states that no straight line, or if we're talking about 3D space and we're dealing with a 3D Bezier curve, then instead of straight line, it's going to be a plane instead. So it states that no straight line can intersect a curve more times than it intersects the curve control polygon. So now let's look at the two images on the right to better understand what the property is. Let's look at the bottom image first because it has a lot of different color and it will make it easier to understand. There's 3 different straight lines intersecting this image. Let's just pick one line to look at. Let's say yellow, for example. Let's count how many times it intersects the control polygon. So it intersects the control polygon 1, 2, 3, 4, 5, 6, 7. 7 times. Now let's count how many times it intersects the curve. 1, 2, 3. So as you see, it intersects the curve less time than it intersects the control polygon. Now let's look at the image right above that. let's pick the diagonal line for this one. Let's count how many times it intersects the control polygon. 1, 2. 2 times. Now let's count how many times it intersects the curve. 1, 2. Also 2 times. So as you see here, it also does not intersect the curve more times than it intersects the control polygon. So basically, this property shows that the complexity of a curve is never going to be more complex than the curve control polygon. All right, now let's talk about some Bernstein polynomials. Bernstein polynomials are mathematical functions that are used to calculate certain stuff about Bezier curve. This right here, we have the recursive definition of Bernstein polynomial. And as you can see, it's a linear mathematical equation. So it's pretty simple to calculate. You kind of just plug and chug a number and you'll be able to get the answer. And if I end up being less than 0 or I end up being greater than n, then the Bernstein polynomial will end up being equivalent to 0. Bernstein polynomial of degree n can be defined by combining together two Bernstein polynomial of degree n minus 1. So you have two Bernstein polynomial of less degree. You can combine them together to create Bernstein polynomial of degree n. And the graph that we have down here is an example of the recursive definition of the Bernstein polynomial. So now that we are done talking about the recursive definition of Bernstein polynomial, let's talk a little bit about the derivative of Bernstein polynomial. So as you can see here, we have the mathematical equation written out for the derivative of Bernstein polynomial, and it's a pretty linear equation. I would like to point out that a Bernstein polynomial where I equal -1 and n equal n minus 1 is equivalent to a Bernstein polynomial of I equal n and n equal n minus 1, which is equivalent to 0. Derivative of the n-degree Bernstein polynomials are polynomials of degree n minus 1 and can be written as a linear combination of Bernstein polynomial. So basically it's saying that if you have polynomial of degree n minus 1, you can combine them together to get derivative of the nth degree. And as I stated before too, it's basically a linear equation. The three graphs down here at the bottom are just examples of derivative of Bernstein polynomial. Now let's look at an algorithm to compute Bernstein polynomial. So due to the fact that Bezier curve have the symmetry of basis function, we're able to create such an algorithm like this. So the algorithm on the left is to compute the value of a Bernstein polynomial at a fixed value u. And the table on the right is a visualization of what the algorithm on the left is doing. So as you can see here, it starts out at many different points, and then it slowly converges down to one point. It basically looks like a triangular approach. So it starts out at a base, a very big base, and it slowly gets smaller until it gets down to the tippy top point. Now let's look at the algorithm to compute all Bernstein polynomial. This algorithm on the left will compute all nth degree Bernstein polynomial for a fixed value of u. And then a table on the right here is a visualization of this algorithm on the left. And as you can see, this algorithm functions quite differently from this other algorithm. This algorithm that we went over already basically start out big and get smaller. However, this algorithm to compute all nth degree Bernstein polynomial will start out at one point and it slowly diverge out to many different points. So it start out small and then it get bigger. Now let's look at that algorithm to compute one point on a Bezier curve. So this algorithm right here will compute one point on an nth degree Bezier curve at a fixed u value. And the algorithm is pretty simple and straightforward to actually write. If you look on the right, these two images on the right are just showing a bunch of points on Bezier curve that you'll be able to calculate using this algorithm. Now, let's talk about derivatives of Bezier curve. So due to the fact that Bernstein polynomial have that derivative property to it, it's very easy to derive this general expression for the derivative of Bezier curve. And you can take a look at the expression right here. On the right, we have two images of example of Bezier curve derivative. So the very top one, as you see the biggest curve right here, that is the derivative of B14 and B24 combined together to be able to create that Bezier derivative curve. And then the image at the bottom is just basically a visualization of actually 4 different derivatives of Bezier curve. I would also like to point out that the derivative of the n-degree curve is an n minus 1 degree curve. So if you have an n-degree curve and you get the derivative of that, you get an n minus 1 degree curve. The n derivative at u equals 0 and u equals 1 are symmetrical. So similar to the symmetry of basis function that was pointed out earlier for Bezier curve. The k derivative at an endpoint depends on the k plus 1 control point at that end. So depending on how many control points you have at one end, the k derivative at that endpoint will be affected by it. Here are two different examples of first derivative and second derivative for derivative of Bezier curve. The top is two examples of first derivative. They're pretty linear, straightforward, not too complicated. The bottom are two examples of second derivative, which are also pretty linear and straightforward. And if you take a look at the derivative for C0 and the derivative for the first derivative for C0 and the second derivative for C0, you can see that it has a lot of similarity to it. It's very similar. Basically, you just add on one more control point, and it's just adding on more stuff to it. Very similar. And you take a look at C1 and C1 first derivative and C1 second derivative, you could also see that's also very similar, and it's just adding more stuff onto it too. And there's kind of like a pattern to how it works. Let's talk about corner cutting process for Bezier curve now. So the corner cutting process for Bezier curve is actually a very popular process. What is corner cutting though? It's finding a point on a Bezier curve through repeated linear interpolation. And a curve can be considered a corner cutting curve if every single point on that curve can be found from a given polygon through a finite corner cutting process. So if you're given a polygon and you basically perform a finite number of corner cutting process on that polygon, and you're able to get every single point on a curve through doing that, then that curve is a corner cutting process curve. On the left here, we have an image example of what a quadratic curve look like that has gone through this corner cutting process, that has gone through repeated linear interpolation. And the idea of this is that basically you kind of like just cut off corners with straight line until you end up getting a rounded curve, a rounded shape that you want. And this is actually a method that's used a lot in like wood cutting. Woodcutter would basically just cut straight line at corner until they finally get it down to kind of a rounded shape that they want it to be. This is another example of a corner cutting Bezier curve. This one, however, is a cubic Bezier curve that has gone through repeated linear interpolation or through the corner cutting process to be able to get the curve. And as you can see here, since this has more points, it has to go through the corner cutting process more, and it has to go through more linear interpolation to be able to get the curve. Descartes-Stillhall algorithm. This is actually a very popular algorithm, and it's a type of corner cutting process. So with the corner cutting process that we talked about before, this is the algorithm that's used to actually implement that. It will compute a point on a Bezier curve through repeated linear interpolation between points in the vicinity of the curve. This algorithm is very popular and is very good because it's less prone to round-off error, and it does a really good job of the corner cutting process. Here we have a visualization table of the points that will actually be generated when the Descartes-Stillhall algorithm has been implemented. So it's kind of similar to the algorithm that was used to compute the Bernstein polynomial for a fixed u. not n-degree Bernstein polynomial, just a Bernstein polynomial. It starts out big with many points and it's slowing it down to 1 point. And then the mathematical equation down here at the bottom below the table is the recursive mathematical representation of the de Castillo-Hall algorithm. And that will be the end of my slide. So Neil shall take over from here.
Now we'll talk about rational curves. In general, rational curves are a way to represent conic curves. With rational functions, we have the ratio of two polynomials. In this case, we can see xu, yu, and wu are the three polynomials of interest. One point to mention is the fact that wu is shared as the denominator between these two equations. Here we have an example of a circle. In this example, the radius is 1, and the circle is centered at the origin. Here we have the two equations that represent that circle. This is a diagram or graph of the circle represented by these two equations. Next, we have an ellipse, which is centered at the origin with the major axis at the y-axis. The minor axis is the x-axis. The major radius is 2, the minor radius is 1. This is x of u, y of u, and the corresponding equations. Again, we have a graph to show the representation of the ellipse. Here we have a hyperbola, and the center of the hyperbola is at 0, 4/3. The transverse axis is the y-axis. Here there are the two equations that represent the hyperbola. And a key point to note is that for the bounds 1 minus square root of 3 over 2 and 1 plus square root of 3 over 2, that is where the lower branch is traced out. And you can see that occurs right there. So if one just wanted to trace out the lower part of the curve, one could bound u by these two values. Lastly, we have the parabola. The vertex is at the origin, and the axis of symmetry is the y-axis, as is most parabolas we have seen before. In this case, we can see that the rational functions are not needed. We can see that there is a division of 1 that is shared between these two polynomials, and there is no need to have this x of u equals u. Here we can see the example parabola. Now on to the more mathematical side. The nth degree rational Bezier curve is represented by c of u equals the summation from I equals 0 to n of the Bernstein polynomial I comma n of u multiplied by the weights multiplied by the control points divided by this summation of the Bernstein polynomial and the weights. We have a bounds of the u value between 0 and 1. In this case, we assume that the weights are greater than 0 for all I, while the weights can technically be negative. For the scope of this class, we will assume that the weights are non-negative. Additionally, the particular values of the weights are not important. What does matter is the variance between the weights to one another. Now we will show the rational basis function. Essentially, we're substituting this portion right here for r sub I comma n. And here, through using some algebra, we have defined the rational basis function and made the substitution for c of u. Again, we have bounds of u between 0 and 1. Similar to the standard Bezier curves, the rational Bezier curves follow many of the same properties. For one, we have non-negativity, where the output of the rational Bezier curves will be greater than or equal to 0 for all I and all n, as well as u being bounded by 0 and 1. We have the partition of unity, where the rational Bezier curve between I equals 0 and n will equal 1. Again, between these bounds of 0 and 1 for u. With r of 0, comma n of 0 and r sub n, comma n of 1, both of these outputs are 1. And the rational Bezier curve attains exactly one maximum on the interval of 0 to 1. And if the weights are all 1, then the rational Bezier curve is the same as the Bernstein polynomial for all of I. More specifically, the Bernstein polynomial is a special case of the rational Bezier curves. Moving on to some geometric properties of rational Bezier curves, we have the convex hull property. The curves are contained in convex hulls of their defining control points, which we labeled earlier as P sub I. We have transformation and variance. Rotations, translations, and scalings are applied to curves by applying them to the control points. Next, we have the variation diminishing property. Essentially, no straight line intersects a curve more times than it intersects the curve's control polygon. In this sense, we see that the curve will not wiggle more than the changes made by the control points. We have endpoint interpolation, where C of 0 equals P sub 0 and C of 1 equals P sub n. The kth derivative at u equals 0 depends on the first k plus 1 control points and weights. Similarly, the kth derivative at u equals 0 depends on the previous k plus 1 control points and weights. And we have that polynomial Bezier curves are a special case of rational Bezier curves. Next, we have an example. In this case, we have a circle. Using this vector notation, we show the first quadrant of the unit circle. This forms the rational Bezier of a circular arc. Again, the bounds of u between 0 and 1. Here we showed the weights of each of the control points. W sub 0, W sub 1 are both equal to 1, and W sub 2 equals to 2. Through some algebra, we can show the different representations of W, U. Now on to homogeneous coordinates. Here we have a rational curve with the common denominator. We use homogeneous coordinates to represent a curve in an n-dimensional space as a polynomial curve in n plus 1 dimensional space. Here we would represent a 2D curve in 3D space. So we will have a point in three-dimensional space represented by x, y, z, and project that point onto four-dimensional space, where we have p to the w equals wx, wy, wz, and w. Here we assume that w does not equal 0. And we'll map that p to the w from the origin to the hyperplane. This is done by dividing these x, y, and z coordinates by their corresponding weights. Essentially, we create weighted control points for p sub I to w equals w sub I x, w sub I y, w sub I z, and w sub I. We have non-rational or polynomial Bezier curve in four-dimensional space. Here we have that representation where we take the summation of the Bernstein polynomial multiplied by these control points represented here. Now we will apply the perspective map using vector notation. Here you can see that the change in the weights of the control point would change how far this projection takes place, and thus change how this curve is represented. Now going back to our circle example, we have the same points and the same weights, but we can see how this weight 2 being equal to 2 shows this increase in the projection so that this control point is raised up. Now we'll talk about tensor product surfaces. Tensor product surface has the following form with S of u comma v leading to this vector xyz with parameters u and v. And this is equal to the summation of these two functions f sub I of u and g sub j of v multiplied by these control points b sub I comma j, which are represented right here. Again, we have 0 less than or equal to u and v less than 1. With tensor product surfaces, we are mapping the surface to a rectangular domain, or I should say from a rectangular domain u comma v. We have an alternate matrix form of this tensor product surface. This was the original form, and now we have this alternate form here, where we're representing each item as an array. Now we have isocurves, also called isoperimetric curves, which are two power basis curves who lie along the same surface and intersect at a point. Here we have an example of these two curves with the intersection point right here. Now moving on to tensor product, we have the product of Bernstein polynomials, which is the non-rational Bezier surface. We take the bidirectional net of control points and products of univariate Bernstein polynomials. While that might sound complicated, essentially we are just taking the summation of these two Bernstein polynomials and multiplying by the control point right here, again with these bounds for u and v. Now we can apply Descalzo algorithm for surfaces. It is very similar to curves, but there are two iterations to account for the additional dimension. Here we can see the functional complexity, or the total number of linear interpolations needed for computing c sub u naught of v and c sub v naught of u. They are very similar with the variables n and m swapped. If n is greater than m, we should compute c sub v naught u first, otherwise compute c sub u naught of v first. Essentially, we want to take whichever variable is larger and perform that computation first. Here we can see an example. Assuming the surface maps to a non-square region, perform interpolations on the larger parameter of the region first. And here you can see how we have the control points and how those control points would allow us to generate this surface here, how we would want to go along the longer direction first before the shorter one. With the rational basis function, we can project four-dimensional polynomial Bezier surface. Here we have s raised to w of u comma v is equal to the summation of these two Bernstein polynomials multiplied by the control points. Again, we have the s of u comma v equal to the summations of the rational basis function multiplied by the control points, and through algebra we can show the rational basis function here. A key point to note is that the rational basis function is a rational function, but is not the product of other basis functions. We have the rational Bezier surface represented here, where this weight 0, 1 equal to 5 was able to change the shape of the surface compared to the surface here. Now we have an example, which is a cylinder. This is a circular arc in the YZ plane, very similar to what we talked about earlier. Here we have c to the w of u equal to the summation of the Bernstein polynomials multiplied by control points. Here we have the control points listed here. And we have c sub 0 and c sub 1. When we have the linear interpolation between these two functions, we're given a cylindrical surface, which we represent here. Two Bernstein polynomials multiplied by one another, multiplied by the control points. Now onto the design examples. In a real-life application, we can actually use a tool called FontForge to make our own fonts using Bezier curves. Here we can see how changing the control points will change the curves and the shapes of the font to suit one's needs. Here is another example of letters A and G.
Part 3 of this PowerPoint will be Geometric Modeling Lab. This part will be where we kind of explore a little bit with different programs that we could use to create different geometric modeling. First of all, let's see how to create Bezier curve using Maya. So right here is a YouTube video link that you could click on to go to YouTube to be able to watch a YouTube tutorial video created by Maya that will show you how to create Bezier curve using their program. I won't click on the video link right now, but if you want to, you could always watch it yourself. However, I will show you some screenshots that I have took of me actually creating the Bezier curve myself in Maya. So first of all here, you will open up the Maya program and you could go to Create Curve Tool, and there will be a Bezier curve tool, and just click on that. Once you click on that, it will basically give you that tool, so now you can start creating your Bezier curve. Right here, I have just created one control point right there. The green spot right there is the control point. So I clicked that point and it created a control point for me. Now, I clicked another point over here, and that created another control point. And with that, it created my Bezier curve for me. And then this blue line right here is basically to control my curve. So depending on how I move this line, left or right, and whether I shrink it or make it bigger, it will change how big my curve is, how small my curve is, and how slanted to the left or to the right my curve is. So I end up just creating a bunch more control points and just change them a little bit to make this long Bezier curve now. And this right here is my final Bezier curve after doing some manipulation and changing and creating. And right here, as you can see in the little red circle that I have circled it, once you're in the program and you finish creating your Bezier curve, you could right click and it will give you an option to choose control vertex. If you click on control vertex, all these purple line will appear, like the line that I have circled in red. So these lines will appear and it will let you actually now change your Bezier curve depending on what you want. So you could tilt the purple line left, right, you can make it bigger, smaller, and that will change the curve accordingly to how you want it. And that right there is how to create Bezier curve using Maya.
I have created Bezier surfaces using Google SketchUp Pro tool. So this tool usage is so easy. This is the UI of the tool. For designing Bezier surface, we have an extension called Bezier surface. As you can see here, these two are the extensions. So I just installed it in my SketchUp tool. Here is the first step. We just have to draw a foundation. So then once we double click on this image, we'll get 3D image and then we can play with this surface. So here is the design of control points and we can just drag and drop by using these axes. So these are the intermediate steps and we can design n number of surfaces by playing with the control points. And I have a video to create the Bezier surface. So I'll just play this. So this is the first step. So here we have references. Thank you for listening.